works this way. Is there a light somewhere?
Так, вот.
Spot.
Spot.
Here in center.
Middle.
Okay, thank you. So, first I would like to thank the organizers for having me for the opportunity to speak here. Title of my talk is mainly dynamic nuclear polarization in silicon, and it's related to a recent effort of trying to make quantum computing in silicon. And this work has been done in the University of Turku in the group of Sergei Vasilyev. There's 3 postdocs, and at the moment we actually have at the moment two PhD students, and there's also collaborators from Japan, Korea, and Leonid Vlasenko from St. Petersburg. So, as an outline of my talk, I will give first some short introduction to qubits and magnetic resonance in silicon. Then I will shortly go through our experimental setup. Then I first go a little bit older data about DNP on the donor nuclei in silicon, what we have measured. And then at the end I will go through some recent experiments where we have managed to polarize the silicon nuclei in certain lattice sites, and we can actually show we can actually identify the spins that they belong to certain few restricted lattice sites simply from the ESR spectra. So first, the motivation is for studying this magnetic resonance methods in silicon is quantum computing. Well, everybody in physics community probably has an opinion about quantum computing. Would it ever be useful for anything, and what kind of machines we are actually able to build, and what it's going to be used to? That's seen in the future. But the key things what we need for these devices is qubits. There are some quantum objects which has well-defined, for example, 2-level system, and they has to be well isolated from the environment. So they have a long coherence time or T2 time. One of the key factors also is that you need to be able to initialize the starting state of quantum being. So you have to sort of like null your computer. You have a starting position. You know that all your spins are in the up or down position or some really well-defined state. Number of qubits should be scalable. So only if you add more and more qubits, you should be able to build a bigger machine. And then, which is somehow also one of the tricky things to cope with, is that the qubits need to interact with each other in a controlled way. So you should be able to switch on and off some interaction between the qubits. You should be able to transfer the coherence from qubit to qubit. So we need controlled interactions. And then at the end, you should be able to read out the output state of the qubits. So spin is a natural choice for the qubit. So if you have simply an unbound electron on nuclei, and these energy levels, they are quantized, so the Zeeman levels in the magnetic field, and it's easy to control the qubit. So you can make rotations simply by applying resonant RF field along the axis on the transversal plane. So first, and a little bit like historical thing, the first demonstrations of quantum computing were actually done with NMR, as you probably all know. So they were liquid state samples at room temperature, really complicated molecules. For example, in this published, they have 14 qubits in a single molecule, and they could all be resolved by the difference in the resonance frequency. So they could address each of these molecules individually. Then, by using the methods of dynamic decoupling, they could control the interactions between the qubits, and eventually they could read out the signal because they have a large ensemble of spins. So the signal is big because you have billions of identical computers which all has the same state. And problem, one of the tricky problems with NMR is the initialization problem. So to the starting position at room temperature, the energy spacing even at really high, like 10 Tesla field, is like tens of milli-K. So at room temperature, you basically have even a two-level system, only half of your population is here. And when you start adding more qubits, you actually realize that the probability that you have a ground state computer in your system, it degrades as exponentially. So it's difficult to scale this method to really large number of qubits. So that's why people want to move to solid state systems, where silicon is one of the candidates. There's also other candidates like this nitrogen vacancies in diamond, but in silicon it's good because it has been used by the semiconductor industry for years. So basically, in natural silicon, you have 3 isotopes which are stable. Most of it is silicon-28, which has it doesn't have any nuclear spin. Then you have some less than 5% of silicon-29, which has nuclear spin of 1/2, and they form this diamond-like lattice. And if this silicon is doped with group B donors, like phosphorus or arsenic, due to this sp3 hybridization, you have this extra S electron, and this will give you a huge hydrogen-like atom, which has about 40 milli-electron volt binding energy. So your wave function of electron will expand, and it will cover a huge amount of lattice size in the crystal. And like this. So it covers something like 1,500 of silicon atoms, its own nuclei, and in natural composition you have about 70 spins which has the nuclear magnetic momentum. So the single spin, so people wanted to go also the solid state system because they wanted to study if it's possible to use single spin in quantum computing, not ensemble of spins. And the really boom has started probably from the Keynes paper in 1998, where he first proposed a method how you could use single spin in silicon, phosphorus spins in silicon, as a qubit, and he described this as a system which can scale up to really large computers. So the idea is that you have silicon, preferably it has to be isotopically enriched, containing only 28, because then you don't have any disturbance from the silicon-29 around this qubit. And the big wave function, the electronic wave function, can be relatively easily disturbed by an external voltage. So you have this kind of gates around here, and if you apply here electrostatic potential, you actually distort your electronic cloud, and you will shift the resonance frequency of the electron and the nuclei, and this way you can actually address this single spin from here. So you can have thousands of spins here, and you can address simply a single one of them. And then you can have several other gates where you actually pull the electronic clouds here towards each other, and then you have a controlled interaction between the electrons. So in this way, it's possible to manipulate a single spin. Of course, to have polarized state, you have to be in rather low temperature, and preferably also your magnetic field has to be of let's say more than 2 Tesla. So there's been some recent experiments where they have found that in electron coherence time in silicon-28 lattice can be easily extend 1 second, and you can control this also with optics and electric field, and of course the methods of magnetic resonance. And then the donor nuclei spin can be reached T2 times of 180 seconds. So this rotating in the plane, it will stay there for 180 seconds. Of course, this was done with dynamic decoupling techniques, so that even without these techniques, the rotation, the coherence time is roughly something like 40 seconds. It's a nice idea, but problem is that the realization is really difficult. You have to be able to build these kind of gates exactly on top of your donors. So it needs some technical engineering skills, which at the moment starts to be available, but not really like sure how it's going to be done. Then people are also interested about silicon-29. So in this case, most of people want to get rid of the silicon-29 because it causes some decoherence in the system. If you have bulk silicon-29 around, far from the donor, there's a flip-flop transition going on all around in your system. This will create some disturbance to your system, and it actually leads to decoherence. And what people has realized also that if you take the nuclei nearby this donor, you can use the silicon-29 nuclei near the donor, and they have about the same coherence times than with the donor nuclei. This has been done in natural silicon, so the coherence time is shorter, but this can be improved by simply installing here several silicon-29 nuclei, and still the rest of the system will be absent of, will be topically enriched to get rid of this bulk background. The second thing what we are thinking about is that if you can create bulk polarization of silicon-29, this could also lead to reduction of the decoherence, because then you don't have any more this flip-flop transition around. So, then we'll come to the experiments what we have been doing in Turku. And we started at 2012, and we used helium refrigerator with a silicon sample, and we have high field ESR spectrometer. We used the magnetic field of about 4.6 Tesla. And then we have some small NMR coils to make Endor and to manipulate nuclear spins. So here's some details of the spectrometer. I don't show them in detail. Basics is that this most of the spectrometer is cooled down to about 1 Kelvin temperature to reduce the noise. It works at something like 128 gigahertz. This is important. We are operating in a continuous wave mode, so we don't do any field modulation or anything. We simply sweep the magnetic field and measure the signal normally. We have also possibility for pulsed mode, but our excitation power is limited to some key components of the spectrometers to about 400 nanowatts. So we can't get really like high tilting angles, but we can do pulse ESR experiments also. The sensitivity of the spectrometer is relatively good, and so with this kind of sample what we have about 10 to 13 spins. So the sample cell, newest version of it is a Fabry-Perot cavity. So we have a spherical mirror here, we have a flat mirror. The flat mirror is made of epoxy, and which is coated with gold. And sample is located on the top of this mirror, and then we have wound directly inside the Fabry-Perot cavity and into the mirror some RF coils to have highest possible RF field. We can't put really high powers for our NMR circuit at the moment because it simply means that we are heating our system. It's in the dilution region. We have a cooling power of something like several hundred microwatts, so we can't put there really huge powers for our NMR. So then, because experimental fact is that if you put the silicon sample here, it will distort your cavity a lot. So at room temperature, you can't see the cavity at all. So that's why we actually introduced here a piezo positioner where we can move this. And when we cool it down below 10 Kelvin, we start to see our cavity. After that, we tune the resonance conditions. This is important because our spectrometer has a rather narrow bandwidth. It's about 1-2 gigahertz where we can work. So if we start at room temperature and put the silicon sample there, it shifts the frequency so much that we can't see anything. We have to be able to control it at low temperature. Yeah, here's just a big glimpse of it. This is the pH positioner, the sample is there, and there's the coils. There's some extra coils also around it. So, I will simply remind you a little bit of this, of the electron spin resonance on hydrogen-like atom, like phosphorus. So basically, phosphorus is spin half. So it has this 4 energy levels. We have 2 allowed transitions. And relaxation time in our field for this is about 0.1 second. And the forbidden transitions are not visible in our spectrometer. You have much higher power to see it. So this is all is applied to a field of something like a little bit less than 5 Tesla. At 5 Tesla, this mixing angle of the state is rather small. So basically, this means that our spin states are relatively close to pure spin state. So important thing is that when you cool this down, because this energy spacing is about 6 Kelvin, so below 1 Kelvin, our electrons are basically all polarized. There is very little occupancy of the upper energy state. So here is a scheme of the spectra. So the splitting of this hyperfine splitting for the phosphorus is about 42 Gauss. And then there is this forbidden transition which are located at this field outside of the spectra. But they are resolved from the spectra. So in principle, you can address them separately from the peaks. So when we start first, this is the ESR spectrum with low power. So we keep the excitation power at something like below 2 picowatts. V1 field is then at about 10 microgauss. Temperatures, we usually work at below 1 Kelvin. This temperature after 1 Kelvin, it only influences the relaxation rate of the nuclei. So if you heat them up, the nuclei spin, they start to relax. And here's an example of arsenic spectra, which is says spin 3/2, and then phosphorus, which is spin 1/2. Then there's some additional features in the spectra, which is some clusters. You have, and then in this sample there was some phosphorus atom impurities. It was not pure arsenic. The line width is approximately something like 3-4 Gauss. Arsenic has slightly smaller line width. And the density of donors in our sample is something like 6 × 10⁻16. So then we go, I just remind you quickly, you all know this, but the methods of DNP or dynamic nuclear polarization in solids. So basically you have 2 effects. First, the Overhauser effect, where you pump the allowed transition so you basically excite your line, and then there is a certain probability that there's a thermal relaxation through the forbidden transition, and if you do this long enough time, you start to have population here. And if your electrons are really well polarized at the beginning, basically you can transfer this electron polarization to your nuclei. So that's actually the ratio between these two at half a Kelvin temperature and 5 Tesla can be 10⁻⁶. It's very good starting point for making any kind of operations for the spins. The second effect, which is the second dynamic DNP method, which is called solid effect, can be is utilized so that you actually excite the forbidden transition, and then you wait here that your spins are relaxing to the state. So you keep this excited, you start pumping, and eventually your nuclear spin will move from here to here. There's actually an error here. This should be a downward arrow. So important thing is that you have to use relatively high field and low temperature to have the electrons polarized. Once you have polarized your nuclei, they stay there. If you keep below 1 Kelvin, the nuclear relaxation rate can be many days. I will actually show you later. So this is one example of our of DNB of the donor nuclei. We started from equal population for these two levels. Then we apply 30 seconds with highest power that we have for 400 nanowatts to excite the line. And after 30 seconds, we see that most of this line has reduced and most of the spin has moved to this state. Then we repeated this a little bit longer, and after about 20 minutes of pumping, you don't have anything here, and all the spins are, so all the nuclei are moved to this state. We can extract this cross relaxation rate time of something like about 15 seconds. This is I will show you in detail. This is actually not so straightforward, but there's a fast part and lower part in this relaxation. So with this way, we can create full polarization of phosphorus. This is also an example, just quite recent data from arsenic. So if we start from this spectra, we have almost equal population of the spin states, and then we simply pump first on this position, then we move the magnetic field here and excite this line, and eventually all the spins are piled up in this state. So we can pretty much control the nuclear movements in our system. So then, important thing is how quickly this actually will relax. So this is for phosphorus. There is a polarization defined like the difference between this lower nuclear states. And as you see here, at different temperatures, if you go above 1 Kelvin, it's relatively fast. And when you start to approach half a Kelvin, it becomes so the relaxation becomes so small that it starts to be difficult to measure. So if you take this and plot this as a function of inverse temperature, you actually find out that the slope coincides with the Zeeman energy of the electronic levels. So the slope is around 6 Kelvin. And this points to a nuclear relaxation mechanism, which is called Orbach mechanism, where you actually have a thermal excitation of the electrons, and then they relax back due to thermal excitation. And key factor is here is that this exponent actually has the electronic energy here and not anything related with the nuclear. And if you you quickly notice that if you cool down your system, the nuclear relaxation can be made so small that it's not influencing your system. So how large an DNB we can make? So if you take simply the numbers, put here reasonable temperature of 0.2 Kelvin, we use the simply dynamic equation of how much spins relax from here and how much they are transferred back to the relaxation. And we get that if we start with the population of 10 to 12 spins in both of these, we will get after 600 seconds with pumping of this 400 nanowatts, we get that only 10 spins are lining back here and all the rest of our pumped are here. So then more about this. So this was the dynamic polarization of donor nuclei. Now we go to the polarization of silicon-29, which are around the donor. So they are influenced by the donor electron, and due to the super hyperfine splitting, they have different frequencies. So here's it's a complicated slide, but here's the full Hamiltonian of the for the donor and silicon-29 spins. There's no interaction between with donor nuclei and silicon-29 taken into account here. And basic idea is that if you have this level splitting, you simply have an extra. If you add here a single silicon-29 nuclei, it will have a super hyperfine interaction, which actually splits these to a numerous state. And if you add there really many states, you see that this UESR line becomes unhomogeneously proordered simply. And these levels here if you want to pump these forbidden levels for the super hyperfine, the forbidden transition is in this field, it's separated from the ESR line about 14 Gauss. So it's well outside your ESR line. So you can really resolve the solid effect transitions. If you are in the lower field, they are mixed up with your allowed transition and you can't separate them. And with phosphorus, the highest superfine interaction is about 6 megahertz. So here, this is simply some example how you can detect this. So you make indoor spectroscopy. So basically, you pump your NMR transition and follow your ESR. In this case, we actually burn a hole and follow how the hole is filled due to the NMR. And this was first time measured already a really long time ago. So then we start DNP experiments with our line. So this is arsenic line, the lowest field line of arsenic, and the temperature is around 700 milligauss. So we sweep our magnetic field here, and we have stopped here, and we keep the magnetic field constant. Then we stay there for about 300 seconds. And after that, when we record the spectra, we see that there's a really narrow hole burned here. And here's a magnification of that. So, and the width of this is something like 9 kilohertz, which gives you roughly T2 time for the electrons of 100 microseconds, which is in reasonable agreement from the literature. And in addition to this, you have also a peak here. So part of this, let's say, spin packets from here has been moved here, which is really right next to this hole. And outside here, it's basically you can't see anything. So it's a single peak and a hole which is burned. And here's an example also for phosphorus. The same thing. The hole here is somehow narrower, but this can be actually in this experiment. It might be that there was some experimental things which actually made it larger. So now we start the question: what happens to the line shape if we polarize all these nuclei around your donor? So or at least we can polarize most of them. So what we do here is we stop at the middle of the line, and we apply some FM modulated signal from our spectrometer. So in this case, it's 3 megahertz, and we keep it there for 10 minutes. Rather small power, medium power in our spectrometer. And after that, we record the line. So the first here is the undisturbed line. And after that, we find out that there's like a window, and then there's a sharp peaks, and really high peak on the right-hand side, and on the left-hand side, there's a smaller peak. So, so during this excitation, we are doing the Overhauser effect, where we pump the spins to this state, and they are actually relaxing. But there is also some portion of the spins which are relaxing back to this side. There's a smaller peak here. Usually, this flip-flop transition is the probability for in Overhauser. The probability for this flip-flop in the Overhauser effect is usually bigger. So how this actually happens then? So in each location, this is continuously kept, the ESR transition is continuously kept excited, so it's saturated. So the spin packets are continuously jumping here, depending on and the jumping distance from each location is defined by the super hyperfine constant, which you remember it was 6 megahertz for phosphorus. So continuous spin is moving here mostly, but most probably it's moving to this direction. And then just at the edge of the window, it's piled up here. And if we do this for the whole line, we can actually create this peak. We can narrow down this peak by a factor of 50 from the original line width. So one question is that all of the spins are piled here relatively near the window. Why? There's nothing here because for 6 megahertz jump, there should be like this much possibility for the spins to jump. But there's really outside the window, there's not so much spins. And so we started to study this. This is a measurement with arsenic, where we have burned this single hole. So it's the same again, about 9 kilohertz. And we show this sharp peak just on the right-hand side. Then we start to add some small modulation. So we put 20 kilohertz modulation, and what we saw here, we produced a hole which is roughly twice of the modulation as it should be. But we start to what start to appear here is that we start to see some peaks on the background of this. And if we increase the modulation further, there's clearly some structure appearing here. So it seems that when we apply the modulation, it enhances the polarization near the donor. Because if your spin is really far away from the donor, the jump is really small. So you pile up having this peak just near your hole. But if you start to flip the most closest spin, you have actually a bigger jump. So you jump from the hole directly here. So we can actually now say that we have polarized some of the spins which are really near the donor, and we can actually detect that this has been polarized. So this is simply a comparison that to this pattern, how it matches with the Endor spectra. And we can see that some transitions we can recognize what they are, but there is some transitions which are not visible. This Overhauser effect creating this peak is what was first of all at the beginning was tricky because we didn't see any of these patterns, and there was some basically we were using too wide modulation because this peak width also spreads when you use wide modulation, so we couldn't recognize it really. Then we went to this. Then let's go to the solid effect, which is actually the most important effect on what we have found. So if you now go outside this allowed transition or lower field line of the phosphorus and offset by something like 14 Gauss, so we're really way out the line, and pump there for some time. So here we pump for 2 hours, and we start pile-upping spins through this method. And after that, if we measure, you see here this black spectra, there starts to be an appearing a pattern. And this is then the green one is simply background subtracted signal. We have simply subtracted this red curve here. And this seems like a long time, but the efficiency of solid effect is only restricted by the available power. So if we can increase the power, we can put it actually to below 1 second, then it should be only limited by the electron relaxation time. How much I have time left?
A few minutes.
Okay, so so we pumped. We noticed also that if we pump this from flip-flip or flip-flop transitions, the patterns are actually identical. There's no big difference. So the probabilities for these transitions are the same for flip-flip and flip-flop. So this is for arsenic, and it's a little bit better result. But what we notice is some lattice sites are not visible here. So for example, here you see that there's A, B, but C shelf, which is located somewhere here, there's no peak. And then we started to study, okay, why certain transitions are not visible. So if you compare, then if you start with the free atom, so you don't have any disturbance from the lattice, you actually the forbidden transitions, if you excite them simply by transversal field, it's not going to work. So you need something for the solid effect. I don't know if the name actually comes from the solid effect. You need the solid lattice to disturb your electronic signal that you have this anisotropic dipolar interaction of. And so basically, as your hyperfine constant can be split to 2 parts, the isotropic Fermi interaction and the dipolar interaction. And then from here, you can actually calculate how your states are mixed due to this anisotropic term, and you can calculate the probabilities for the solid effect transition with different spins. And if we compare this for phosphorus and the location of when the magnetic field is at 111 direction, and you see that this is stronger interaction, and this is a probability that you excite this transition with solid effect. And for example, the C shell, it's visible, but yeah, it simply means that the C shell, it has really small anisotropic interaction. And from here, we can further manipulate these spins, because now we can say that these spins, for example, they belong to a certain lattice sites around our donor atom. So we can later on apply NMR to manipulate these spins. And we can read out the detection for IESR from these peaks. So this is my conclusions, and thank you for your attention.
Thank you very much. Please, questions? Dr. Järvinen.
Very interesting work. Excuse me for a stupid question. I learned that Michael in Stuttgart tried to apply to create pure electron spin states by more-dimensional EBR spectroscopy. I forgot the name. Michael Mehring. Can you compare your approach with his result? Because I learned from his work that it was very difficult to realize pure spin states.
I'm not familiar with his work, but if he works at the low field EPR, if it's not...
No, he was working in the high field. Yes.
The temperature range was... he was working about 1 Kelvin temperature range.
Yes,
then it starts to be tricky. Because the key point here is, in our work, is that you have to be below, you have to be well below the splitting of your G-man levels. So then you get like a free of charge electron polarization. And
Yes.
then you can transfer this easily to the population of the domain. So the only thing which is tricky is that the combination of low temperature and high fields and
Yes.
high power, that's tricky.
Yes.
So we are still lagging here higher powers, which we would like to make some pulsed experiments.
Yes. Okay.
This tool we'll try in future.
Yes, yes. Thank you very much.
Any questions, please? Sorry? No. I have another stupid question. In any computer, we need to have strict determination of calculations. And quantum mechanics gives us the probability of the event. How can you comment this problem?
Well, basically it's like, well, eventually you try to create some kind of algorithm that you have a well-defined starting state. Then you have certain problems which you want to solve. And there's numerous ways how you can do it. So in principle you can do it with the classical computation. But you have this quantum mechanical sort of like analog bit. The dimensions which you are accessible at the same time, they are really like huge compared to classical computing. And this way you can the system will evolve to some state, and you know the dynamics how it goes because you control the dynamics. And then the readout.
But we should have a big ensemble of particles also, yes?
Yeah, it can be.
Besides the very huge experimental details.
So it of course, if you have only a few qubits, it's not so interesting. You can play around. So you really need like big thing. But if you can make this system so that you can actually control all these interactions, it's like you can build your Hamiltonian how your system evolves, and you can simply say, okay, I want this state and how it evolves, and then I will read out the state. So it's sort of like a quantum simulator.
Thank you. Another questions. Thank you very much again.